Alright, I want to take a look at a few of these physics problems I assigned. I've had a few emails about them already, which is good. I'm glad you guys are seeking out help. Okay, I'm going to do a couple of them, and hopefully that'll help you out on the rest of them. I picked a few that maybe have a couple different parts in them. Okay, so the first one I'm going to look at is number 90 on page 82. Number 90 says, a race car can be slowed with a constant acceleration of negative 11 meters per second. Okay, so as always, we start by listing what we know. So acceleration equals negative 11 meters per second. Okay. If I read part A, it says that the car is going 55 meters per second. So that's where it starts. That's my initial velocity. V naught is 55 meters per second. How many meters will it travel before it stops? Okay. It wants to know how many meters, so that's a change in position or displacement. Before it stops is my final velocity, 0 meters per second. So there's every piece of information I know. Now I just need to figure out, what do I do, right? Well, I've got final velocity, initial velocity, acceleration, and change in position. I have an equation that relates all those. Kinematic equation number 3 says final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. Okay, so plug in my variables. 0 equals 55 squared plus 2 times negative 11 times delta x, and fact that 55 squared over, and so it becomes negative 3025 equals negative 22 times delta x. Divide both sides by negative 22, and we get delta x equals 137.5 meters. Okay. So that takes care of part A. That's how far it moves. Part B on that one said, how many meters will it take to stop a car going twice as fast? Okay. Well, if it's going twice as fast, that means its initial velocity is equal to 110 meters per second. Other than that, everything stays exactly the same. So 0 equals 110 squared plus 2 times negative 11 times delta x. Okay? And you'd think it would take twice as far, but that's not the case. And so 110 squared divided by negative 22 is 550 meters. Okay? Delta x equals 550 meters. What's the true relationship between those? Well, figure it out. 550 divided by 137 is equal to 4, or 137.5. Okay. Why is it 4? Well, it's proportional to the square of velocity, not to velocity itself. Since we doubled the velocity, 2 squared is 4. Okay. So that's number 90. Number 91, okay, is a little bit different, but not bad. Number 91 says, a car is traveling 20 meters per second when the driver sees a child standing on the road. Okay? So that gives me my initial velocity, 20 meters per second. Okay? She takes 0.8 seconds to react, then steps on the brakes. Okay? That gives me a time interval of 0.8 seconds. Okay? During this time, nothing has changed, so I have a very constant velocity. So I'm going to go ahead and put a square around that. She takes 0.8 seconds to react, then steps on the brake and slows at 7 meters per second. Okay? So now I'm going to have a new time interval. V naught is still 20 meters per second, but now she has an acceleration of negative 7 meters per second. It's negative because it's opposite her motion, and I assumed her motion was positive. Okay? And we're supposed to find how far she goes before she stops. Delta x equals what? Okay. Well, because there's the constant motion part and the accelerated motion part, we have to do this in two separate problems. And here's why. Okay. If we were to take a graph, that was almost a straight line, right? If we were to actually think about the graph of this motion, and I'm going to do a velocity time graph, okay, for the first little bit, she is cruising along, and she's got a constant velocity of 20 meters per second, okay, for 0.8 seconds. She sees the kid but hasn't had time to apply the brakes yet, so that's a straight line. Then it says she slows down at a rate of -7 meters per second for the next little bit. Okay? Because this time interval is, or these two motions are different, it's not a constant acceleration, we have to divide it up into its two blocks. Okay? So that's why we have to divide that up into two intervals. So we're going to say during this time interval, this is pretty easy. This is the second kinematic equation, x equals 1/2 at squared plus v naught t plus x naught. Okay? Except really I'm just looking for a change in position, so I subtract that x naught over. So I got x minus x naught, which is delta x, equals 1/2 at squared, except for the first part of this, there is no acceleration, so this term drops out. So this is just v naught t. Okay? So change in position equals initial velocity times time when there is no acceleration. And so I can take 0.8 times 20, and this is 1.6, not 1.6, 16 meters. And so she goes 16 meters before she even starts to apply the brakes. Then she starts to apply the brakes, and I want to know how far she goes. Well, if she's going to stop, I also know final velocity is equal to 0 meters per second. So I can say v squared equals v naught squared plus twice the acceleration times the change in position, which works because I don't know time. If I knew time, I could just do the 1/2 at squared, but I don't know it. Okay. All right. So here we go. Final velocity is 0. Initial velocity is 20 plus twice the acceleration, -7, times the change in position, which is what I want to know. So 20 squared is 400. We subtract it over and we get -400 equals -14 delta x. Divide both sides by -14 and we get 28.6 meters. Okay? Our 16 meters from up here plus our 28.6 meters down there tell us that she moved a total of 44.57 meters. Alright. And finally, I said I was going to do question number 112. This one is a little bit more complex because it's not just one moving object, it's two moving objects. And so 112 says a truck is stopped at a red light. So over here I'm going to list everything I know about the truck. It's stopped at a red light, so its initial velocity is 0. When the light turns green, the truck accelerates at 2.5 meters per second. So acceleration 2.5 meters per second per second. At the same instant, a car passes the truck going 15 meters per second. So a car has an initial velocity of 15 meters per second. Okay? Where and when does the truck catch up with the car? So this is also kind of handy to look at in a graph first, I think. Okay? But this time maybe a position time graph is more intuitive than a velocity time graph. Okay? Here's what I know for sure. I know that there is a car that's moving at a constant rate of 15 meters per second. So a constant rate on a position time graph is just a straight sloping line. I'm not scaling it, but there, we'll say that slope is 15. The truck, on the other hand, is moving with a velocity that's changing. It started at rest, so it's got to be fairly flat, and it's getting faster, 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 faster. Eventually it'll catch up and pass the car. We want to know when and where that happens. So we need the time t and we need the position x. And if we can figure that out, we'll be done. Okay? Well, here's what we know. We know that the position of the truck is given by x equals 1/2 at squared plus v naught t plus x naught. But since we're measuring everything from the traffic light, we can say its initial position is 0. Okay? Same thing with the car, we're measuring it from the traffic light, its initial position is 0. It says it's moving constant, so its acceleration is also 0. And so if we put these two, well, let's get this other equation. Okay? The car, its final position, or its position at any point in time, is given by 1/2 at squared plus v naught t plus x naught. Okay? Let's sub in all the information we know. Okay? Well, I know the acceleration of the car is 0, so that whole term is gone. I know it started at 0, so that term is gone. So I know x here equals v naught t. Okay? Up here, I know x equals 1/2 times 2.5 times t squared, but this term is 0 and this term is 0. Okay? Now what I'm really interested in is where these two things are in the same place at the same time. So I'm going to take these equations and set them equal to each other. I need 1/2 times 2.5 t squared to equal v naught t. Okay? Handy is t is on both sides. Oh, and I know v naught, right? I know v naught is 15. I'm like, wait a minute, that's two unknowns. I'm going to run out of equations. Nope, we'll be okay. Okay. So v naught's really 15. All right. I've got t on both sides, so I can divide this side by t and this side by t. And so now I have 1/2 2.5, which is 1.25, times t equals 15. Okay? Divide both sides by 1.25, and I get a time of 12 seconds. T equals 12. Okay? So I know when. I know that this time right here, when they intercept, that's 12 seconds after the traffic light turns green. Okay? What about where? Well, just pick one of these two equations and put in that time. I'm going to do both to show you it works for both. Okay, so for this one, my initial velocity was 15, so if I take 15 times 12, I get 180 meters, right? If I come up to this point, 144 times 2.5 times 0.5 equals 180. And so it totally works out. They are the same. Okay? Just don't make silly calculator mistakes.